Okay, good to go.
Okay, welcome back to another VC Libraries Open Code Review. I am Stefan T. Lauade, an STL maintainer, and today we'll be looking at a PR from our contributor Adam Bussior. It's PR 2158, extend memcpy, memmove, and memcomp optimizations. Here we're looking at our code reviews project dashboard. This shows the various stages that PRs go through until they merge to our repo. We have a process where when a PR is finished being changed by the contributor, we have one maintainer do an initial review of it. And as we iterate on it, I move back and forth to work in progress. When everything looks good to that first maintainer, we send it forward to final review, and we have a second maintainer double check everything for perfection. This ensures that if we miss something, it was really subtle. And this catches a lot of issues before they actually get fixed. As I always like to say, we like to be lazy by being thorough. The more thorough we are during review, the less work we have to do fixing bugs. And reviewing is a lot more fun than fixing bugs. So I'd rather do more reviewing and less of the bug fixing. And so that's why we've got all these columns here. So this will be the first time we're looking at Adam Bussior's PR. Adam has contributed several features and optimizations to the STL in the past. This is actually a follow-up to previous PRs that we've reviewed. So I will now switch over and look at this PR and go to pull request. Okay. So this is addressing an issue. We had been sort of translating our various to-dos that we had been scrolling away in Post-it notes and to-do.txt and things on internal SharePoints to GitHub issues, because everything should be on GitHub. And this performance issue mentioned that the copy and fill family could engage memcpy, memset in more cases. So this is something we had increasingly noticed as we were looking at the STL's code base. This is something that is sort of invisible, but we've considered important, and it's surprisingly useful. It sort of reduces the what's called the abstraction penalty of calling the STL. So the STL provides high-level algorithms like std copy, std fill, that work with arbitrary element types. And these are really cool because you can copy into a range of integers, into a range of std strings, or your user-defined custom types. And it's going to work the same way. It's going to perform, copy assignments as necessary. However, if you're working with something like just a range of integers, there are these functions, the CRTs memcopy, memset, memmove, memchure, and so forth, memset, that are typically implemented with very special assembly code that's constantly being updated by people who work on processors for a living. And they expand these special sequences of assembly that are what I like to say faster than the core language, meaning that they can do things that the compiler would not ordinarily generate, like special sequences of vectorized instructions, seeing how big a chunk of memory we're going to copy, and if it's over like 4,096 bytes or something, call special AVX intrinsics or whatever. There's a ton of effort that goes into making those things as fast as possible because they're used so often by programs. So if std copy just expanded to ordinary loops in the CS+ core language, then the compiler would generate, pretty optimal code for it, optimized code, but it would not necessarily generate the super efficient memcpy implementation, even for things like ints. So what we have historically done is we have used template metaprogramming, which sounds scary, but it's really just sort of simple logic done through templates that detects the element type and the iterator type and says, oh, if the input range is like int star and the output range is int star, then I know that we're working with contiguous sequences of integers. There's no possible user-defined types, no non-contiguous iterators, bidirectional stuff. It's just pointers. So I can just totally call memcopy or memset or whatever necessary function I need at compile time, select that at compile time, and then at runtime it'll expand to the optimal sequence of code. So we have made this increasingly elaborate over the years by activating it in more cases, unwrapping iterators. So if you provide vector iterators, yeah, those are user-defined types where the user is the standard library, but we unwrap them down to raw pointers and then detect, oh, it's just ultimately an int star and we can call memcpy. We've been using if-const-expr to simplify our implementation and avoid emitting so much debug code gen with our old technique of tag dispatch that's increasingly been replaced. We've had to add additional logic, though, because now things like std_copy are now const-expr in CS+20. And that means that because the memcpy CRT function is not const-expr, we need some logic that says, hey, if we're constant evaluated, which is a special magic function that the compiler provides, we need to write the classic loop in the core language so that the const_expr evaluator can handle it. But if we're not constant evaluated, meaning we're at runtime, then we can activate our metaprogramming and say, okay, if we're at runtime and if the types and iterators are eligible, then call memcpy. So there's a bunch of layers, and yeah, it's a lot of complexity. That's why we hide it all in the standard library, so users can just call std_copy and get efficient code. So what this issue tracks is that there are even more cases where we could activate this optimization. And there's some cases where we need to perform a static cast, like to unsigned care, because that's what memset does. And if that happens to be equivalent to what a plain assignment would do, then users wouldn't be able to notice the difference. So that is what Adam Bussior is tackling in this PR. We had filed this PR fairly early on in our open source journey, January 2020, and it has now been addressed. So this is a large PR. There are 3,700 lines of additions, 789 lines of removals, or just source lines being changed. This is generally larger than I would prefer to see in, like an ideal vacuum. It's easier to review smaller PRs, but some changes are just like inherently large. In this case, there's a whole bunch of refactoring going on. And Adam Bussior has worked extensively on this code in the past. So the bigness of the PR is not itself problematic, but it is going to be challenging to review because when this much code is changing at once, we need to be very careful that nothing is being lost. One of the ways that we end up being lazy by being thorough in the STL is whenever we're changing code, we try to make sure that we avoid regressions. Because the worst thing is to change code and go mess up something, and now you've slipped backwards in an area, and then users notice regressions and they report, hey, the code is wrong or it's buggy and so forth. And then we have to go, fix the regressions. So regressions are pretty bad. Whereas if we improve things strictly, then we're just cranking up our quality, and we don't need to fix things retroactively. At most, we might notice, oh, okay, there's a place that we missed that could be even better, and that's fine. That's in fact sort of like how this PR is working. We're extending previous optimizations, making the STL even faster. We just need to avoid any regressions doing so. So whenever I see code being changed, I'm going to be trying to look at it and see, okay, are we retaining the previous behavior as much as possible and where the only changes, the behavioral changes that are happening are ones that we expect and ones that will improve things. It's okay to have changes like to the form of an optimization or to the form of machinery that don't ultimately change the observable behavior, especially if that becomes simpler to follow or more consistent. But we want to look for any semantic changes when this happens. And I've caught a whole lot of regressions over the years, noticing when code is being transformed in a non-equivalent way, especially with templated code. It's very possible to slightly rephrase the code in a way that starts mishandling some bizarre user-defined type. And with enough familiarity with templated code in the STL, it's possible to look at that and say, wait, this isn't going to handle types with an overloaded operator address of, or this won't handle movable only types under a full moon, on a certain day of the year. So that's some of what I'll be looking for. In the case of these optimizations, things to reason about are where things like the usual arithmetic conversions happen. That's very relevant to things like std_fill that needs to call memset. For memcomp, we need to think about all the possible types that can be compared, like care, signed care, unsigned care, bytes, and so forth. If they're volatile, all these different possible inputs, both at runtime and at compile time. So let me read through Adam Bussior's summary here before I start looking at the code. Okay, and this is wonderful, by the way. Having a detailed PR description that describes what's happening is amazing. This way, we don't need to sort of review the actual code changes and then try to divine the intent of them backwards from the actual code. That can be very hard to determine, like, why is this code changing at all? And the fact that there's a human readable explanation of the intent of the changes is excellent, because that way, when we see the code changing, we can look at it and immediately see, oh, okay, this is the part that handles the second bullet point. If I see any code that I don't understand why it's changing, I can come back to this description and try to educate myself as to, okay, is this necessary to implement one of these bullet points? Is it a drive-by cleanup that should have been mentioned in the bullet points? Or is it an undesired change? In which case, I may have found an actual issue. So this is awesome. With PR, especially, like, it's okay if a small PR is just like, fix bug and then doesn't elaborate. But with a large PR, having it just be submitted without any explanation is not just challenging, it's sort of hazardous and dangerous, because there could be a mismatch between the developer's intent and what the code is actually doing. And if you weren't the developer who wrote it, it can be very hard to notice that mismatch. I have had personal experience, years of reviewing code without descriptions that are extensive, and it is quite risky. So this is awesome. Thanks, Adam. Okay, so product code changes. And I love that it's divided between product code and test code, because the product code is the one we're very, very careful with. Test code, a little bit less careful. Still want to be somewhat careful. So extended the memcpy and memmove optimizations. These functions differ in that the memcpy CRT function cannot handle any overlap. The memmove CRT function can handle arbitrary overlap, according to the standard. In our implementation, they're actually secretly the same thing. They both handle overlap, but we shouldn't take advantage of that. So extended these optimizations to not require is trivially copyable and is trivial, which are slightly different type traits in the core that reflect core language properties, but just is trivially copy constructible, trivially move constructible, trivially copy assignable, or trivially move assignable, depending on the operation. Okay, so this is making it more fine-grained. This will have no effect for the majority of simple types like ints or a struct containing ints, but for unusual types, for example, where maybe the move construction just copies bits around, but the copy construction goes and logs something, or vice versa. Or maybe the class has trivial copy constructors, but when you copy assign, it's got a user-defined operator that tries to handle references or something. We've got some of those in the STL itself. Then we will begin activating that optimization, making it more fine-grained by using the right type traits. Okay, so that makes sense. Then renamed our somewhat old and confusing putter copycat and putter movecat to iter copycat and iter movecat, because they no longer work only on pointers. This is reasonable. It's a little bit of like a, aside. It's not strictly necessary, but the fact that these are now increasingly misnamed, it's reasonable to make this change at this time. Cat here means category and not kitten, despite our love of everything feline in the STL. Fixed move iterator handling in memcpy memmove optimizations by specializing to address for it so that it doesn't warn about deprecated move iterator operator arrow. Okay, so this is a good bug fix in reaction to recent standard changes. The standard deprecated move iterator operator arrow, we implemented that warning, but we were accidentally internally using it to grab a raw pointer. So now Adam's going to add a specialized underscore to address helper. This is ugly, so it's internal. That will unwrap move iterators down to the raw pointers. Okay, so that just fixes a deprecation warning. Extended the memcpy, memmove, and memcomp optimization to handle pointers to pointer interconvertible types. So this is a new CS+20 feature that was implemented in C1xxbar compiler dev Jonathan Caves. And it's also available, I believe, in Clang and EDG for IntelliSense. This can answer questions like, I have a struct of int and double. The int is the first member. There's no other weirdness in that struct like virtual member function or anything. So that first int is actually at the same address as the struct itself. So although they're totally different types, if I reinterpreted between them, I would have physically the same address. So these are what are known as pointer interconvertible, if I am describing it correctly. And because the guts are the same, if you are memcopy, memmove, and memcomping such things, and there's no extra data member, so like here it would be like a struct containing just an int and a plain int. Those would be pointer interconvertible and the same size. Then there's no reason why we can't just memcopy. I mean, yeah, we're not really respecting the type system, but all the bits will be in the right location. So this is an optimization that's possible now that we have this type trait. Before we had this type trait, which is powered by special compiler knowledge, we couldn't ask, oh, I have a pointer to an int and a pointer to a struct. Are these contents literally the same? We couldn't do that. We don't have like powerful reflection or anything, but the compiler knows, so it's going to tell us. We've got another helper function, is all bits 0. This is now being special cased for the null putter t type, which just inherently is all bits 0. So that seems reasonable. Refactored lex compare memcomp classify, which is used to determine can we activate the memcomp optimization in lexicographical compare. So that's being refactored because it has accreted complexity over time and extended it to bools. Okay. Extended memcomp in lexcompare 3-way, which is the new spaceship comparison, to handle comparators like strong order, weak order, and partial order. I believe these are the comparator functor objects that I implemented, finishing Casey Carter's implementation of the spaceship machinery. And these comparators were not being detected as special. So it makes sense that, oh, you gave me a library defined comparator, but I know that it's just going to, call spaceship on ints or whatever. So why not just call memcomp? So that makes sense. Extended memcomp optimization to handle non-transparent functors. So this refers to another feature that I worked on. The transparent function objects are what I proposed for CS+14 that look like less diamond, just empty angle brackets. And they can accept arbitrary types, perform their comparison or operation like less than or plus, and then return whatever that returns, rather than trying to coerce the argument types to a common type. So memcomp and whatever, this is now being extended to the classic function objects that are non-transparent, so like less int and so forth, or when the types differ. So here, for example, to enable optimization in equal when using int, unsigned int, and equal to int. So this is a case that we currently don't optimize because the types are different. But when you convert an unsigned int to an int, the bits actually remain the same, especially now that CS+20 has mandated 2's complement representation for signed integers. So although there is a value transformation here from large unsigned to negative int, the bit pattern remains the same. So performing that equal operation with a non-transparent functor can be replaced with memcomp. It requires a lot of reasoning. This is one of the special cases I mentioned, but that is valid. We need to be very careful because if these types were narrower, this would not be possible. For example, I could spin up a compiler explorer example to show. If you compare, but here I know the answer in my head, I'm like 99% sure. If you have a negative int, like negative 2 billion, and you have a large unsigned int, like 4 billion unsigned, and you compare them for equality, the conversion, in this case, if you compare them with equal to int, the unsigned int of 4 billion would be converted to negative 2 billion. And then, pretty sure I got that right. I might get that wrong. They'll be converted to negative, let's say. And then if the int is the right negative number, it would be equal. However, if you try to do this with smaller types, that would not be the case. If you had short and unsigned short and gave them to equal to int, that has the necessary range. If you had short, unsigned short, and equal to short, you would be okay because there you would be specifically coercing, converting unsigned short to short. If we allowed the usual arithmetic conversions to happen, it would be promoted to int, and we would get the behavior of, oh, okay, the int has enough range. So this is a very tricky area. Need to spend extra brain power to make sure that's right. This also enables memcomp optimization with enums when using a functor that converts them to their underlying type. Okay, interesting. Do we have such a functor in the standard library? We don't. But if there's a function object that emits that, we can detect what it emits. Okay, I think some of the range algorithms might do that. They've got projections. Next, disabled memcopy and memmove optimization for volatile, because volatile says, hey, don't optimize this thing. I want actual physical reads and writes. Totally reasonable to disable. We haven't had users complain because volatile is quite obscure, but it is the right thing to do. And then enabled memcopy optimization for const destination in a whole bunch of algorithms, both classic and ranges, uninitialized, copy and move, also the n variations that take a specific number. And there's a related issue. Uninitialized meow should handle voidifies wording. Yeah, there's some wording here about a voidify helper that returns a modifiable void star. You can construct const elements in uninitialized memory. Yeah, so it looks like this partially handles the case, although it doesn't completely resolve the issue, which is why Adam just mentioned it rather than using GitHub's magic wording to fix the bug. Test changes. Removed a VSO test. This is our internal bug database. It's a fairly old bug because it's only 6 digits, put or cat. So it's an old test. I can tell that just from the number. In favor of a more detailed bugs for GitHub 431 iter copy move cat, equal memcomp is safe, and let's compare memcomp classify. That seems fine. It's about time to sort of refactor that test. Inspired by Phil family, added GH-431 copy move family, equal family, and lex compare family to test that all the optimizations work well. Okay. Also making sure that compilation with custom contiguous iterators continues to work. He's moving that test to the equal family. And then fixed a test const expr algorithm in exchange to define all the necessary type defs and output pointer. Sometimes we have tests that define types for use by the standard library, and oftentimes we'll we try to be good, but sometimes we miss something and we define only the necessary types that make it compile, and we don't technically meet all of the requirements of the standard. This happens a lot with allocators, and I'm always finding allocators that don't quite meet the requirements. We try to fix them up. In this case, we must have missed something in output pointer where we didn't define all the necessary type defs, so having this fixed is very welcome. Okay, so that's the description. And the background. That took a while, but it's a large change and there's a lot of background here. Our contributor Misko has reviewed it and talked to Adam a little. There's some stylistic questions. Here's a question, why aren't these structs aliases, but we need to specialize them? So yeah, this explanation makes sense. We can use aliases when we have no need ever to specialize. We just want sort of a convenient way to refer to stuff. I'll give that a thumbs up, and I will go ahead and resolve that because there's definitely no action to take there. Let's see. Yeah, is trivially constructible V? Yeah, the core language does this. It's trivial in the sense that it doesn't activate any user-defined functions. The core language is transforming the bit. I think the difference is that is trivially constructible does not mean that the bits are unchanged. I think that's right. Honestly, like whenever I look at the is trivial traits, the whole family of them, I'm like 80% sure how they work. It's sort of related to the details of the core language that I'm not a super duper expert on. Our contributor Alex Guteniev is noting that the different tests do consume test execution time. That is true. We've got a lot of tests. This is proportionally not a very big contribution. I don't mind this too much. Certainly we don't have like tests one per function. That would be like tiny little test per function. That's not our style, and that would actually bloat our test execution time significantly. In this case, there's a lot of functions in each family. The families are somewhat different. So having them separated in a test is probably better. I think it's worth the increased test execution time. If we ever need to go refactor the test and consolidate some of the smaller ones, we've got some real small tests that are old that we could consolidate or clean up. And yeah, the ones that have like lots of instantiation coverage or sometimes context per evaluation, if it starts to threaten the compiler running out of memory, that's problematic. Even if you have enough memory, we run as many of them at a time as you have processors. So I agree with both our contributors here. It is a concern. I think it's a valid way to have separate tests here. So I will give them both thumbs up, and I will comment there is definitely a test throughput concern with having lots of small test directories. Actually, I will begin by saying I agree with both of you. Smile cat. There's definitely a test throughput concern with having lots of small test directories, but in this case, I believe that it's reasonable to have separate directories for the reasons that Adam stated. Okay, I agree with both of you. There's definitely a test throughput concern with having lots of small test directories, but in this case, I believe it's reasonable to have separate directories for the reasons that Adam Busier stated. Okay. Yeah, that sounds reasonable. I definitely appreciate Alex Kutenev keeping an eye on how many test directories are being added and whether the test throughput concern is problematic, because our tests are taking increasingly longer. That not only makes our development a little bit slower every time it happens, but it also increases the load on our PR CI checks machinery. So far, it's not like threatening to consume more than our monthly quota, but it is something that we do need to think about using responsibly. In this case, I think it's responsible use. Okay, so I commented there. Okay, and that's all the comments so far. Good. Let's begin looking at the code. Okay, so we've got 21 files. Going to alt-click to minimize them all. See what we get. Okay, so we've got product code changes. The biggest one is 454 lines in xutility. Not surprising. This is the STL central-ish header for algorithm stuff. All the interesting ones like copy and fill, especially ones that need to be used by containers or elsewhere throughout the STL, tend to be centralized there. Whereas if they're not needed by the rest of the STL, they tend to appear directly in the algorithm. We've got some test directories being changed, and then all the tests being refactored. Okay, so that's why the PR is so large. It's all the test refactorings. The product code changes are on the order of 500 lines, which is not nearly as scary as 3,700. Okay, so this is good. Let me just check the mechanical stuff first, the new tests. So here are all the new tests being added. They're in sorted order after dev 11. The lowest number before was 457. So that's good. And they are lexicographically sorted, IJKL. Yes, that all looks good. Okay, I'm going to quickly double check the names. Copy move family, equal memcomp safe, iter copy move cat, let's compare family, let's compare memcomp classify. Okay, let me check the names here. So that was what, 6 of them? Yep, 6. So for the new test directories, copy move family, equal memcomp is safe. Iter copy move cat, let's compare family, let's compare memcomp classify. Okay. Those all look correct. I don't see any typos or whatever. Here I double check it because test.list is only used by our internal test harness. So typos here would not be detected until we actually run this internally. So this looks good. Have any test directories been deleted? Yes. Puttercat. This is the one that was being renamed. So this is going away and all the others are new. Yes. Do we have any other test directories being deleted? No, these all look like pure additions. And here's the puttercat that's being decomposed. Yeah. Okay, so test.list is correct. Awesome. Okay. I'll come back to the test later. Let's do product code first this time. I always like to leave the hardest stuff for last, so let's look at all the small files first. Our way up. Okay, so in algorithm, we got some of the renamings. So in each case, it's putter copycat to iter copycat, putter move cat to iter move cat. So it's just putter to iter. So I want to make sure there's any copy pastos. The damage during mechanical changes is very scary. So I try to, even though it's tempting to tune them out, I try to slow down and think, okay, are we seeing the same thing every time? And 99% of the time, it's exactly the same as expected. And 1% of the time, you find that one copy paste mistake that would have been a real bug. So this is good. Putter copycat to iter copycat. Here, trivially copyable is changing to an internal bool trivially assignable. That's because we're doing copy n, and that is doing assignment. So this is a good change. We're going to see what the definition of it is later, but that name makes sense. For the move algorithm, we want the iter move cat and trivially assignable. Yep. For move backward, again, iter move cat, trivially assignable. This is, I'm assuming, lex compare. Yes, the internal helper lexicographical compare unchecked for the ranges function object. This is being simplified. Previously, we asked what happened if we call this helper function, what type would it return, and then look at its nested pred. Now there is just a, I believe it's a struct, not an alias. So this is nice and simple. This pattern was correct, but definitely strange and not usually what we do in the STL. So the type def name is unchanged, but we just say lex compare memcomp classify, give it it1, it2, and PR instead of the actual objects there. We're reusing the name. This was a function. This is a struct. Any use of renames, we always need to think about, is this going to pose ABI issues? I believe none, because functions and structs are mingled completely differently. And if it's being converted in a single blast, then don't need to worry about like mix and match scenarios or confusion during the rename. I think that's fine. These are just being re-indented because of claim format, aligning the equal, so that's all good. I don't see too much more of that. If I did, I would turn on ignore white space in the little gear here, but so far I'm going to leave that off. Next, looks like a renaming plus rewrapping for claim format. We have iter copycat. This is the helper for ranges uninitialized copy. So it's iter copycat. And instead of asking really trivial, we're just going to ask, are you trivially constructible? Because we're not going to do any assignments. We're just going to copy into uninitialized memory, which is constructing. That seems right. Then we rewrap this. Yep, that looks good. We've got this empty comment here, which forces a claim format wrapping. Claim format is not the best at handling variable templates right now. So retaining that seems right. It certainly looks good the way it is. Rename iter copycat. This is again in uninitialized copy n, so trivially constructible. That looks right. If context for iter copycat. This is, are we still in an uninitialized helper? This is uninitialized copy n fun for ranges. So we're being given an n, but it's still an uninitialized copy. So iter copycat trivially constructible. That's right. And then this automatically rewraps. It's good. Now we're in uninitialized move n. So we have iter move cat. We're moving into uninitialized memory. So trivially constructible is correct. If context for iter move cat. Let's see, it's presumably another uninit move n. Yes, uninitialized move n. So iter move cat trivially constructible. And then this rewraps. Okay, so that's all good. Vector, just a couple changes here. Assign range. So if we're in vector assign and we detect that the iterator range given to us is forward iterators or better, we can detect how many elements are in that range, resize our vector in a single action, and then update elements as necessary. If we're given only input iterators, we don't know how many elements they're going to be until we consume them, so we have no choice but to repeatedly place back, which is actually up here. You can see it's a lot more code. We have to destroy stuff and then in place stuff because we can't do any better. But this is optimized. This is still using our tag dispatch technique. Eventually, we could probably make this if const expert. We've got a tracking issue for that. So, and yeah, definitely, we would not want to see that in this PR. This PR is already quite large enough. So keeping this existing structure is definitely the right call. So putter copycat to iter copycat, yes. And now what are we going to do? We are assigning. So we're going to try to reuse as much existing capacity as we can. Sometimes we're going to have enough. Sometimes the new size coming in is going to be less than or equal to the old capacity. But if it's greater, then we need to clear out the vector, reserve sufficient space, and then clear and reserve geometric. Oh, it's because we're assigning. We're not doing an insertion. We're just replacing the entire content of the vector. That's why we clear. So if we have sufficient space, we will be assigning over existing elements. That's the copy unchecked here and here, depending on whether we're increasing size or decreasing. We'll destroy any unnecessary elements, and if we need to increase size, we will construct in uninitialized memory. This will also handle the case where if we needed to reallocate an entire buffer, then this will do nothing, and all of the constructions will be in uninitialized memory. So we need two possible actions. One is assigning over existing elements or constructing in uninitialized memory. That's why we need this dual test of you got to be trivially constructible and assignable. So this is exactly correct. And yet it's still more fine-grained than asking the entire type to be trivially copyable. So that's good. And that's the end of the changes there. Same change down here. What's going on here? This is move assign with unequal allocators. In the case where the allocators are unequal and we cannot propagate allocators, so this is a relatively arcane case, but it means that we're move assigning two vectors, their allocators cannot deallocate each other's allocations, and we're not allowed to assign the allocators themselves to propagate them. So we actually need to be allocating memory despite the fact that this is a move assignment. So we're going to try, it's very similar to assign, in fact, which is why we've got the same change here. We're going to try to reuse as much memory as we can, but sometimes we've got to allocate more. So in the case we allocate more, we need to construct. If we can reuse existing capacity, we assign, and that's why we have trivially constructible and assignable. So this is good. This is excellent. It shows that Anna has put a lot of thought into each change and is getting exactly the right trait every time. So really appreciate that. And yes, same types being fed. The type trait is just being renamed to iter copycat. That all looks good. And it's asking copies here instead of moves. Okay, changes to vector, good. X memory. Okay, this one. Similar to the algorithm that we saw, this is focused on the uninitialized algorithms. Uninit moved unchecked. Putter move cat changes to iter move cat. Really trivial changes to trivially constructible because we're constructing in uninitialized memory. That's good. Putter move to iter move. Really trivial to trivially constructible for uninit move unchecked. Yep, we're constructing in uninitialized memory. This rewraps. That's all good. Putter copycat to iter copycat, trivially constructible for uninitialized copy. Yep, that's good. Putter copycat to iter copycat, really trivial to trivially constructible, again for uninitialized copy. Yep, we're constructing. Uninitialized move, putter move cat to iter move cat, trivially constructible. Okay, that's all good. Okay, changes to XString. Okay, we've got a comment here, but it's imitating the existing comment. Okay. So we used to have We used to have a variable template named pred is consistent with memcomp. That's going away. Now we have a variable template named can memcomp elements with pred. This is being specialized, but it's being partially specialized. So that's okay that it's InlineBar. There's this gotcha that gets us every time we mess with inline variables, it seems like, where in CS+14 mode, it is technically undefined behavior to have an explicitly specialized variable template because we don't have inline variables in CS+14 mode. So the pattern is if we see template, empty angle, diamonds, followed by the capital InlineBar macro, that's a bug. But if it's a partial specialization, we're okay. Or if it's CS+17 or above, where we can just say plain inline, we're also okay, even if it's an explicit specialization. So this is fine. It's just whenever I see InlineBar, I always think of that because the compiler doesn't warn us until we're too late. So here, instead of saying that the pred is consistent with memcomp, we're going to just answer, can you memcomp elements with pred? It's still being specialized on the same thing, but we're going to answer, you can memcomp elements with pred if the elements are the same and the character traits, EQ is our struct wrapping char traits. We ask, okay, can you just memcomp the elements themselves? Because char traits EQ is not going to do anything different. There's a transition comment saying that technically this is not quite right. If there's user-defined specializations of std char traits, that may do something different. We just commented it because we think that's super duper obscure and nobody's actually doing it in the wild. So this is being extended in addition to being renamed. Here, library provided char traits LT less than behaves like less of make unsigned T of elem. Yes, that sounds correct. Does it compare like unsigned? I need to check this. I don't actually know. So let's load this. This is in strings library, character traits, character trait specializations, and somewhere around the requirements. Okay, here we go. xltcd returns whether C is to be treated as less than D. Is there anything here that says it's going to act like unsigned? Because plain char is signed. Okay, I don't see anything like that. This is just doing actual less than. Pretty sure if char is signed, that I'll get less than. Oh, I should have minimized that. I don't know. I don't know if this is accurate. Let me see what char traits LT does.
It just directly uses a less than. From
okay,
what I
just
see.
on the character type.
Yeah,
okay, is that
yeah, that's in XString around like 195 for the plain char traits.
STL repo. There we go. String 195. Okay, thanks.
Yeah.
Yeah, and this is less than arbitrary elem. Yeah, we just operator less than. This is is this a general specialization or the primary template? It's the thing that powers the primary template. Yeah. And for like char traits char, do we end up using anything different? This is the W char traits for wide stuff. That one's less concerning because our W char T always acts as unsigned short. But it's plain char that can be signed or unsigned depending. Here's the narrow char traits that derives from the thing we just looked at. This will be used for char and char AT, as the comment says. We provide compare length find, but we don't. Oh no, here's LT. Oh, here we go. So for narrow chars, we do static cast. And for the wide ones, they already have unsigned behavior. Okay, that's very interesting. I was mentally remembering the 195 line, and I had forgotten about this one, if I ever knew about it. So I believe Yes, Adam Bussior's explanation here is correct. It's either wide, in which case it's unsigned, or if it's narrow, we end up with the narrow char traits that does this. So excellent. Today I learned something. Transition. This should not be activated for user-defined specializations of char traits. Yep, same rationale. Super duper obscure. I doubt that's ever going to be an issue. And if so, we can file an issue and fix it. We do have the technology to detect whether something is the library provided template or if it's a user specialization. We basically do something like add a type def, and if we add an internal type def, and if we see that type def, then we know we're looking at our code. And if we don't, on like stood char traits, we're like, whoa, that type def should be here, but it's not. This must be a user-defined specialization. So it's a very limited form of reflection. But because it's extra work, extra machinery, we have only used it when we anticipate that it's going to be an issue. So I'm totally fine with imitating the existing code here. So template on class LM. Let's compare memcomp classified pred for LM char traits LT, char traits LM. ULM is a helper, that's make unsigned T. The pred, which is what we emit, is going to be conditional. If we classify, let's compare memcomp classify elements, ULM, then we can use less int. If we can't, then use void. And this is the existing protocol we've used elsewhere. This all looks right. We emit less int. Why do we emit less int there? Should that be, I'm trying to figure out, should that be less ULM? Let me look again at the STL and see if this is an existing type. No, okay, so this must be new. Okay, this must be from xutility. Okay, so I'm going to actually, before I mark that file as viewed, I want to see how this is used, because I want to understand why are we seeing less int there? Should that be something else? Okay, so we're looking for this thing, because it's going to emit from pred either less int or void. Okay, so for arbitrary elements and preds, we emit void. Void is definitely the, I don't want to do this optimization. For LM1, LM2, and some arbitrary less LM3, if the LM3 would use memcomp and copying from LM1 to 3 and from 2 to 3 would be trivially constructible, then emit less int. So less int is being consistently used as the answer of, I want to use memcomp here. Let's see where we actually check this. Sometimes we emit greater int to indicate that the comparison should be reversed. But we're not actually going to do, not actually going to use it in any way. We're just using it as a helpful tag. Okay, this is coming back to me. I think this is imitating an existing convention we have. Yeah, let's compare memcomp classify will then emit that. Yeah, so that's where we get the, right, so that comes out of this. There's a lot of uses of this. This one, this was the function, and this is now memcomp pred. We ask if it's not being avoided or not void. Okay, here's where we use it. So it does need to be int. The reason why is we've actually got this, excuse me. We've got this clever trick here. We call memcomp no matter what. But if we're supposed to do a greater than comparison versus a less than comparison, we need to flip the sign basically of what memcomp returns. So we apply that type that we computed, either less int or greater int, to the answer versus 0. So if it's answer less than 0, that's normal. But if it's answer and we apply that to greater int, we'll reverse the comparison. So that's why it's specifically less int and greater int and not some tag type. It's like less and greater already do what we need, so why have an extra tag there and have the if const expert? So that's an existing trick we have in the STL. I just needed to confirm and remind myself that that's what we're doing here. So less int is correct. It should not be less ULM or anything like that. Okay, so that's the end of XString. Okay, and that's why we're doing that unsigned here. Okay, I think that's good. Okay, that's the product code up to xutility. Let's see how far we can get through xutility. Okay, here's that specialization of moveiterator that was called out. This is why I really appreciate having that detailed PR description. So this is templated on class underscore kept iter. Let's see, it's no discard because its purpose in life is to return something. Const expr, auto, whatever this type is, underscore to address. Take a const moveiterator, iter, ref underscore capital val. It can't be const because it's not a member. No except, yep, because it always just gets a pointer. Return, call to address on whatever the internal iterator is, val.base. Yep, should not be ugly, or it should not be strict qualified because it's ugly. That looks good. Okay, so that's going to avoid calling that operator arrow. Okay, then more change. So this is, the diff is extremely difficult to read because, well, not all of it. Like this is easy. This part's not so bad, but like this here, where we've got the rename, but also substantial changes, this diff is not really helping. So here I want to use side-by-side form, which I don't usually use, but when I see changes like this, it's useful. What I really want is sometimes I just want to see the after change, but currently we can't do that here. Okay, so we've got to address, which we looked at. Now, got a helper. This is replacing, or we're going to get around to replacing puttercat helper. We've got template on class underscore kept iter. We have an InlineBar const expr bool. Because this could be CS+14 mode, excuse me. Underscore capital iterator is volatile. We ask, okay, iterator, what's your reference type? If you are a reference, an actual built-in reference, remove that, and then are you volatile? Okay. Here we use that instead of value type because value type by convention is not CV qualified. If you have a constant star asking through iterator traits its value type, will just give you int. But the reference type would be constant ref, then this would remove the ref and then ask, are you volatile? So that looks good. It's a nice high-level way, rather than having to think about extracting the ref and then removing it and looking at volatile. Okay, so now template on class underscore capital source, class underscore capital dest. It's an interesting order. Should it be dest source? No, usually we say source dest. I think that's what we did elsewhere. Yeah, we said source dest for puttercat helper. Only like the assignment traits do dest source. Okay, so that's good. InlineBar const expr bool. So this is underscore capital is pointer address convertible. We ask, is the source void period or is dest void? Okay, I'm looking at this, I'm thinking, should this be a disjunction? Disjunction can be friendlier for the purposes of throughput. It wouldn't be too hard to convert this into disjunction. On the other hand, it's not massively important. It can always be refactored in the future. There's enough going on in this PR already. I'm okay with this as is. I'm not even sure if disjunction would be valuable here. So if source is void or if dest is void, and then a comment. Note, is same v is required for function pointers to work. Because if we rely, even if we were guaranteed we had is pointer interconvertible base of, I'm assuming that this does not report true for pointers to functions. So here, Adam Booster is asking, are they just literally the same type after you remove any top-level CV qualifiers? Okay. I think that's reasonable. And then if we have the CS+20 CPP lib is pointer interconvertible, then also ask that. Here this says best source. Let's make sure that that is the right order. Is pointer interconvertible base of V? Base of V. Is dest the base of source? Because going from a derived source to a base destination would do an implicit conversion. I think that's right. I always double check the order here. Anything that's order sensitive. Let's see what the standard says. Yeah, of course, that's just the helper variable template. This is a new type trait, so I'm not familiar with it like the existing ones. Oh, it's just in type relations. Here we go. That search didn't get it because it was wrapped with a hyphen. Okay, so this is an elaborate form of is base of. Interesting. Okay, so it is, you've got to be is base of, and you've got to be pointer interconvertible. So you can't add extra data members. Okay, so this acts like the usual is base of that I'm familiar with the additional restriction of being pointer interconvertible. Okay. So is dest the thing we're going to the base of source? Yes, that is the correct order. Okay. Ndif, cplib is pointer interconvertible. Yep, looks good. Looking at that, there's no typos there. Okay. Okay, next, a struct. Misco asks, could we use variable templates here? And Busier says that we're grouping this stuff in a struct. It is a bunch of related things. I like the grouping. I think I agree with that in Busier. I'll give that a thumbs up. Okay, template, class underscore capital source underscore dest, source ref, dest ref, struct trivial cat. The cat that is so simple. uSource is the source with any enum unwrapped. Same with udest. We've done that too. Here u means unwrapped rather than unsigned. Okay. Now we have a static context for bool. Are you same size and compatible? Okay, so it's a bunch of restrictions. First, got to be the same size of source, the size of dest. And then if udest is bool, uSource also needs to be bool. Right. Because like copying a char into a bool could create bools with non-zero or one values. I think this is good, although I would recommend a comma there for clarity. Oh, this looks weird just because it's so narrow. Where is the suggestion? This thing. Just because it looks weird to have bool and uSource next to each other. If udest is bool, comma uSource also needs to be bool. Okay, that's good. Okay, next, conversion from non-bool to non-bool, or bool to bool, or bool to non-bool is fine. It's just the going from non-bool to bool is not fine. Okay. I think separating these with pipes is fine. It's a little weird. It's not too weird. Okay, I'm trying not to nitpick the comments too much. Okay, now, oh, this is interesting. So we're comparing the bools actually with greater equal. If is same v bool uSource greater equal is same v bool udest. This is going to promote the bools to ints and then compare them with greater equal. So this will forbid the case of the source not being a bool and the dest being a bool, which is the one that was forbidden here. I don't know if I like this, mostly because promoting bools to ints and comparing it, this is a highly atypical thing. It is certainly terse. Let me think. So we could phrase this differently. We could say we could express it as a or with or and not. We could say, let me think. The one we want to forbid is where uSource is not a bool and dest is a bool. Yeah, uSource is not a bool, dest is a bool. So we'd say, and either uSource is a bool or dest is not a bool. It would end up repeating these the same amount of time. We need some parentheses. It's not horrible to compare the bools with greater equal. The more I think about it, the more I'm convinced that it's okay. I wouldn't have personally written it myself, but I can't really point to it and say, you know, this is wrong. This is like fragile or something. It's slightly not conventional, but I think it's okay. Yeah, because otherwise we'd have like not and or. We've already got some of that. I'm sure Adam thought about the same thing as he wrote this. I'm okay with it. I'm a little hesitant, but I don't think it's going to encourage weird code. I think getting any more elaborate with bool to int conversions, I would be nervous about. This seems fine because they're really only 0 or 1. The promotions are reasonably straightforward. Once we start doing things like adding bools, then I get a little nervous. I'd want to see like static cast int or something. That'd be another way to prepare this, or to make it very clear, is to add static cast int, but that's very verbose, and I think we'll be fine.
Do you think it would? Do you think it would improve anything to phrase it differently? Like you were talking before about like considering a disjunction instead of a conjunction. Like this is stated as same size and compatible. I guess I'm wondering if this is already like the name of this variable is already kind of a conjunction, so I guess it makes sense to.
Yeah, that's a good question. Yeah, I think it does follow the name because we first test size, then we test compatibility. I think that part is fine.
Yeah. Yeah, yeah. I was just trying to think of, it's like, this is, depending on how this is used, I guess it's like, if it was to be like, if it's not both of these things, if we could improve any flippings, but I don't know if that would actually help.
Yeah, it could be like extracted into a helper, saying we're going to express, is the conversion, like is conversion from non-bool to bool, and then write it out here. That could be a way to refactor it. It would end up being more lines of code. It would increase clarity a little bit, but also verbosity, and that's like close enough that I'm like, I'm willing to roll with what we've got here.
Yeah, that totally makes sense. Just thinking through, even if it's a little bit abnormal, it's not like taking lots and lots of cycles to like parse exactly, especially with the comment there above it.
Yeah, the comment is what really helps. If it was uncommented, I'd be very nervous. I'm like, oh, that's very strange to just, have some ordinary code and then, whoa, it's a bool to int conversion with greater equal. But introducing it sort of sets up, okay, we're going to look for this one specific thing. Why is it greater equal? Oh, that implements the specific thing.
Yeah.
Okay. Okay, so after that, then we're going to ask, finally, a few conditions, either after unwrapping enums, the source should be the same as the dest, or they both need to be integral. If they're integral and same size, and there's no bool weirdness, that's fine. Or after unwrapping, and in this case, enums are never going to unwrap to floating point, but it's fine to always just process the U version. If they're both floating point, then that's fine. Okay, do I agree with that? Exact same size, forbid bool weirdness, literally the same type is always good. If they're both integral and same size, it'll catch things like unsigned short and short, unsigned int and int, unsigned int and long, that's all fine. Or if they're both floating point, float and float would be the same type. So this will catch double and long double for us, which is reasonable. All the other things would be different size or already handled by the same size or same type. That's fine. And it's phrased in the general manner. Whereas having to express double, long double, or double, or vice versa, that would be more logic. Okay, so this is good. This is self-explanatory enough. I don't think it needs to be further commented. Okay, so that is same size and compatible. And then this is reuse. So there is some having it extracted. This is already extracted, so it can be reused later. So this is dramatically increases the readability of the following bools. Static context per bool, trivially constructible. You got to be same size and compatible, and the dest needs to be trivially constructible from the source ref. Trivially assignable, similarly, yep. And then trivially constructible and assignable, answer both of those, yep. Okay, that looks good. The savings, I think, from extensively disjunctioning it would be fairly minimal. And because this is a struct, repeatedly asking this, it'll be computed once for every combination of types. It's not going to be computed like at every single call site. So I think this is fine. We can always micro-optimize the throughput later if necessary. Okay. Now some special cases. So template source dest, source ref, dest ref, trivial cat. If the source and dest are themselves pointers, and source ref, dest ref, okay, then we can answer some things more quickly. So it's trivially constructible if is pointer address convertible source dest. Is that the right order? It was up here. Yep, source dest. This does that base of check. That's saying, okay, if we convert these things, is the address going to be good? That it doesn't need some pointer adjustment. That's why we have used pointer interconvertible base of, because it's not just enough to be base of. If you have a derived to base conversion, that can totally do a pointer offset adjustment in the case of, extra data members being added, multiple inheritance and so forth. But pointer interconvertible base of says, hey, if I convert these pointers with like static cast, do I get the same answer as a reinterpret cast? And it is saying, well, handle a case like, int to int. Okay. Okay, so when we're answering it for pointers, okay, I'm trying to avoid getting confused here. Source and dest are ordinarily elements when they're passed here, but in this specialization, we're absorbing pointers. Is it okay to drop the pointer there? Pointer interconvertible base of. Yeah, when the elements themselves are pointers, we need to ask the derived to base relationship on what they point to. Okay. So here, the elements themselves that we're going to be copying around are pointers. We can do that if the things they point to are pointer address convertible, and attempting to construct dest star from the source ref, and this has not been stripped of pointerness, that is trivial. Okay, this looks right. I have to really slow down and think through, okay, are we removing and adding pointers in all the right places? Because the nature of template metaprogramming is it can be hard to untangle what happens later if things go bad. And make sure that when the time comes to review tests that we're going to cover the right things in the test coverage. Okay, trivially assignable. Okay. This begins by asking, is pointer address convertible? The pointed to source and dest, same as before. And then is trivially assignable. Here we're not constructing a fresh dest star. We're going to assign to an existing dest ref. So if that assignment is trivial, this looks right. And then trivially constructible and assignable, yeah, both constructible and assignable. Okay, no copy paste. If we ever need to immediately answer false, then this provides 3 static context bools. Not eligible. That's the same order as before. Good. Okay, so now this is looking really horrible because of the side-by-side. We have a template on stuff struct iter move cat. Okay, that's what this is doing. It's templated on source iterator, dest iterator, and a bool are contiguous because we're going to be specializing on it. We're contiguous when the source it and the dest it iterators are contiguous, and the source it iterator is not volatile, and the dest it iterator is not volatile. Okay, so we need contiguous iterators and no volatile iterators because those are bad. And those ask, is the pointed to thing volatile? We saw that way up here. Yeah, the pointed to thing being volatile. Okay, and this is general, so it'll work for arbitrary contiguous iterators, not just pointers. Struct iter move cat. This derives from trivial cat, so it's going to get all the answers that the trivial cat gives, and we're going to give it the value type of the source iterator, value type of the destination iterator, and then the references that we're going to be manipulating. The source, because this is a move cat, we're moving from the source. So we take the iter_ref_t of the source it, which could be something like int_ref, an L value reference. We strip referenceness from it, and then we add ref_ref. This is correct. If we did not remove reference, then the L value referenceness in here, if any, would be infectious. So we do need to remove ref before adding ref_ref. That's good. And then we're just going to be assigning to iter_ref_t dest it, because the movingness doesn't affect the destination. However, if the iterators are not contiguous, then false. We definitely cannot use any sort of optimization. That's good. And this follows our preferred pattern where when we have a bool in a template, we prefer stylistically for the primary template to provide the true case because that reads the most naturally. This is the case for when they are contiguous. Okay. And another specialization, excuse me, template, source it, dest it. If we're asking for a move iterator wrapping a source it, even if the iterators are not contiguous, because move iterator would disqualify, for move iterator, we're going to give it a second chance. We're going to say, hey, we'll ask you what happens if you directly worked on the underlying iterator moving, because that's what move iterator is going to do. So this repairs the optimization for move iterator. Yep, that looks good. And because it unwraps, there's no way we're going to wind up in some infinite loop or something. Yeah, you could have a move iterator that would unwrap the necessary number of times. Okay, iter copycat is very similar, so we can go a little faster here. Template on source it, dest it are contiguous. Source it and dest it need to be contiguous. Source it not volatile, dest it not volatile. Iter copycat is trivial cat, get the value types of source and dest. Trying to make sure no copy pastos here. The iter_ref_ts of source and dest. Okay, and we don't need to do any like ref_refing here because it's a copy. Source it, dest it. If you're not contiguous, then totally false. But if you're trying to copy from a move iterator, that would report, hey, you're not contiguous. We'll try to rescue this, and we're going to answer, sorry, do the underlying iterators qualify for moving? Because the move iterator is going to do that. So this is correct. This is very nice. This is easy to follow. Once we get through all the the preamble, the logic that it's replacing that we originally had was quite complicated. It originally had, I worked on this years ago, this complicated interplay between the sort of struct template domain and the function template domain, where we would call a function template and then we would ask, hey, what's your decal type? Or we would use it for tag dispatch in the real old code. And we had all this extra layers to handle pointers and pointers to const. and now that's being sort of subsumed by this type traits manipulation that's happening. Yeah, it's with struct templates, but we're not bouncing back and forth between functions and structs. So this is a lot simpler to follow, even though it looks like a lot of code. I was responsible for adding some of the historical complexity to optimize various cases. So I'm glad that it's finally being cleaned up now that we have better technology. Okay, so we are at iter copycat, and it's replacing copy memmove. I'm not focusing too much on what code is being replaced. Just trying to make sure that any new code is handling what I know what the old code did, because I'm more familiar with what the old code did. So then this begins replacing stuff in iter copycat. Is this just use? So we're at line 4005. How much remains? This is a lot. We get to the lex compare. Yeah, significant refactoring there. Okay. But it's not, doesn't look like wholesale code movements. Okay, I think this is a good pausing point. I was on line 4005 here. So far, we only had the one comment, which was a comma. Very, very boring. So everything here has looked really good so far. That's excellent. So I think, should I add a comment to say that this is where I have partially reviewed? Yes, I think I'll do so, just as a good reminder to myself. Note to self, reviewed xutility up to this line. Up to, but not including, not inclusive. Okay, that's great. I think I'll go ahead and submit this review. I won't mark the file as done. So we're partially through xutility and then all the test coverage. Despite my hesitation at seeing the size of the review at first, this is looking quite solid so far. I haven't found any metaprogramming issues, despite the significant complexity of the code being altered here, which just shows how extensively experienced Adam is with this code by now, having worked on it in the past. So really appreciate this PR, and it's definitely improving a whole bunch of things. So I will go ahead and write that here. Thanks. Looking good so far. I've partially reviewed the product code up to leaving a note to myself. In a video review. We'll continue reviewing this here. Smile. Okay. Thanks, looking good so far. I've partially reviewed the product code, leaving a note to myself where I paused in a video review. We'll continue reviewing this later. Smiley cat. Okay. Yeah, says something about the quality of the review, and the only thing I can find is a missing comma that is not even maybe technically necessary, but would make me feel better if it's there. So that's great. Okay, I think that does it for this video review. We may be seeing this in a future week. If there are any questions, then feel free to let me know. And otherwise, we will see you next time.
I think I voiced the only questions that I had and no one else has showed up. So I think we are good. I'll stop the recording and transcription. And